Good morning. I'm so glad that so many people are willing to come out on a very, very cold Saturday morning. It's really wonderful to see so many familiar faces and a whole bunch of new faces. So welcome. If you're here for the first time, my name is Andrew Zwicker, and I get the distinct pleasure, of serving you bagels and coffee and donuts. And yeah, that's right. So you should know, this is why they're really here. They didn't come to see you, they just came for this. And I just noticed that, by the way, no matter what time I come, and I come earlier and earlier and earlier, there's no bagels left. There's no donuts left. We know what's going on here. Um, and so, as always, thanks for your patience as you come in. We've got, as some of you know, we've now changed a little bit. So microphones in the aisles will also pass around a microphone after the lecture. And then while asking questions, for those of you who can hear me who are on Zoom, I'll check the chat and make sure those questions make it to our speaker today. It is my absolute pleasure to introduce you to Professor Kristin Dana from Rutgers University. You can see that she's gone to school at Columbia, Cooper Union, and is now a full professor at the Department of Electrical and Computer Engineering at Rutgers just up the road, and the co-founder of Steg.AI, a startup focused on watermarking and authenticated digital media. If you could somehow stop deep fakes, we would really appreciate it. She's a recipient of a 2025 Edison Patent Award from the Research and Development Council of New Jersey. And as you can see, her research, and you're going to hear about today, is in computer vision and robotics. Would you please welcome Professor Dana? So I ask 3 questions, but this year it's 4 questions to everybody. So starting it off, would you share with everybody when you personally first got interested in science and engineering?
Okay, I guess my mic is live. So it was early, it was in my teen years. I couldn't decide what I wanted to be when I grew up, and I was deciding among journalism, I like to write, and science. And one of my cousins worked in Bell Labs and talked to me about all the things that happened at Bell Labs. And my parents told me, wow, Bell Labs is credited with a patent a day. And I was hooked. And I thought, oh no, I'm going to leave aside my writing. Turns out as a scientist, you do a lot of writing. So that was good. Yeah.
So how about a teacher from elementary school through grad school that's memorable, had a significant influence on you?
Yes, so many. It's very difficult to name one, so I'm going to name two. One is Professor Bose. When I was doing my master's at MIT, I had the honor of having Professor Bose, yes, he made the Bose speakers, as my professor for acoustics, and he was amazing. And one day he did a lecture, and at the end of it, he said, I don't like the way that came out, and next time we meet, I'm going to do that lecture all over again. And I thought that sense of being humble was a good lesson. Then there's my grammar school teacher, Mrs. Simon, who made science interesting by having science baseball, where she asked questions and we got to say whether we wanted to go for a single or a home run with the science question. I like that.
So when you're not doing your research, you're not teaching, what's something you like to do for fun?
So I like to run. Um, I wake up early and I run at 4 miles 2 or 3 times a week, even in the cold. My record is a 5-degree run.
Did you run this morning?
I did not.
Last question. So this is the 75th anniversary of the Plasma Physics Laboratory. What was your field like 75 years ago?
So 75 years ago, I wasn't in the field, but but I have been a computer vision scientist for a long time. And it's unbelievable that just getting an image to work with on the computer was a big deal. You had to ask around, who knows how to use the frame grabber, which would grab an image from the camera and put it onto the computer. And then, your first job as a graduate student was to learn how to use the frame grabber. And our goal of being able to understand images, recognize them the way you and I do, seemed like a far-flung, long-term goal, but it's here.
Well, thank you. And with that, the stage is yours.
Thank you. Okay, so I will talk about deep learning for embodied AI. And what is embodied AI? Well, for the most part, it's robots. We tend to think about robots, sometimes including automation. So the robots that paint cars or assemble cars in factories are kind of automatons the way our washing machine is automation. There's a lot of engineering involved. I don't mean to dismiss that. But it's much more difficult to have a robot come to your kitchen or my kitchen or someone else's kitchen and cook an egg in that varied environment. There you need AI. And so that's the name of the topic today. So AI actually has three parts. Recently, with the advent of large language models, ChatGPT, AI has become synonymous in a lot of people's minds with ChatGPT. But that is just one component, the language component. Right? There are two other, the way I see it, two other pillars, vision and action, which a lot of people think about as robots moving and manipulating in the world. So this trio, language, vision, and robotics, form AI. And modern robots are embodied AI. They span from human-looking robots, the kind of thing we think about probably from science fiction. When we think of a robot, we think of a human robot. But there are many types of robots like drones. Smart buildings can be considered AI. Autonomous vehicles. The autonomous vehicles of today are robots. They can act in the world, and they need some type of artificial intelligence. And delivery robots. So my field is robot vision, also called computer vision. So what can vision do, right? And how does that translate? How does that relate to action? So a robot can ask, what do I see? And this is the field of image classification. Right? An image, it goes in, and this thing gets processed, and out comes the label dog. A robot can ask, what do I see at every pixel? Not just one word to describe the whole image, but every pixel. Where is the table? Which pixels in the image are the table? Which is the curtains? Which is the dishwasher? That's the problem of semantic segmentation. And the robot can ask, where is the object? And this is a fundamental task in computer vision and robot vision, which is to reconstruct the 3D world from 2D images. And more recently, again, reflecting this link between vision, language, and actions, robots can ask, what should I do based on what I see? And there's one of the algorithms in this space is reinforcement learning to do robot navigation and manipulation to take action in the world. A good illustration of what computer vision can do today is shown here in this CMU's open pose, where video is processed and an understanding of where the people are and what their pose is, the skeletal representation of of their movements, in addition to the representation of their facial expression and hand gestures, is something, the question of 75 years ago. So even 30 years ago, this would be shocking that this can work in real time. Okay, a brief history of computer vision. So I love to give this slide to my students because many of them are from New Jersey, and the rest of the world doesn't know, or the rest of the country doesn't know, I think, that New Jersey is the center of technology, not Silicon Valley. And so if you look at the timeline, right, this timeline of computer vision, many of these key milestones happened right here in New Jersey. Pyramid processing by RCA Labs and then David Sarnoff Research Center and then SRI where I worked from right out of grad school under Peter Bird, was a key moment in this multi-scale processing that also led to image stabilization that we now have as chips in our cameras that stabilize images. Real-time motion estimation, ImageNet, which was the foundation of deep learning, happened at Princeton University with Fei-Fei Li's group, creating this massive crowdsourced data set and changing the game for image recognition, for the scale of image recognition in particular. Let's see, there we go. In the 1980s, Jan LeCun at Bell Labs creating postal digit recognition. The project was to recognize all of our handwriting on envelopes to automatically find the zip code. And it was quite the project. And Jan LeCun used deep learning in the 80s to create a system to do that. And that was the precursor of modern deep learning, right here in New Jersey. Okay, so will the 2030s be ubiquitous AI? It certainly looks that way. Deep learning revolutionized the field. So in computer vision in the early days, we didn't do deep learning. And even when it came in the 80s and showed some remarkable success, the computational power was still so, it was such a requirement and such a difficult requirement to achieve that deep learning kind of had a pause. And then I like to say that I think the gamers subsidized the chip industry and allowed deep learning to reemerge. So if deep learning changed everything, the first thing to ask is, what is deep learning? And sometimes I do a show of hands, but so over the years, the number of people who've heard about it increases. So a show of hands, how many have heard about deep learning? Yeah. A show of hands, how many understand what it is? Yeah. No, it's each year it gets more and more. So we start with the basic element, the biological neuron. And here's where I say I'm an engineer, not a biologist, so I might say things wrong. But the basic idea behind the biological neuron is that signals are received at the dendrites. And when that received signal is large enough, the neuron fires, meaning the output signal along the axon becomes larger. And we can think about this as signals in the brain. And it's waiting until the input is large enough, and then it fires. So we know that our intelligence in the brain at the fundamental unit is perhaps this neuron. So early days of deep learning put together the perceptron, which is a weighted sum. And I love to kind of pause there and say, that's the deep reveal, that's the deep computation. In a neural network, a weighted sum. So those of you who have computed your grades, and some classes are weighted more than others, and computed that weighted average, that's what the perceptron is doing. And then there's a nonlinearity. When it gets high enough, you move from a B to an A. Right? So the weighted average analogy is quite good. Now the perceptrons have been around a long time. The weighted sum is the main computation. It couldn't do that much. It turns out that if you arrange these in layers, where the output of one is the input to the other, and then add more layers and more layers and more layers, and if you put it like this, it becomes deep, then you have a deep neural network. And that's where interesting things began to happen. This network is called a ResNet, a very popular neural network that we still use a lot today. So with neural networks, what the field of computer vision was able to do is put in an image as input. Right? You might say, well, how do you put in an image in a computer? Well, an image, once it's digitized, is a set of numbers. If you then just arrange them row by row as one big vector, It's just a set of numbers, and computers, of course, can handle sets of numbers. And then do the weighted average many times. Even without that vectorization, you can keep it as an image, do that weighted average through a process called convolution. If you major in engineering, you'll learn what a convolution is. And do it again, and do it again, and do it again. Again, this layering is critical. At the end, do a weighted average into a smaller vector, right? And have each node for the classes that you're trying to recognize. You have to know in these networks what you're trying to recognize, like dog, cat, car, desk, what's there. And the numbers in those nodes, you just look through and see which one is the maximum one. And the maximum number is the recognition result. That's it. And that's why the output, if it's correct, is dog, because the dog node was the highest number. So it needed massive amounts of training to create this recognition, but here's what it accomplished. So this, wait, let me just get to this. Yeah, there we go. Do you see how I'm changing the pose of the dog and the network just says dog, right? This is called geometric invariance. And for 30 years, computer vision scientists tried to develop methods to do geometric invariance. You and I are, as if we think about being non-scientists for a moment, it's not very impressive. You know, if we have a dog at home and the dog turns its head, we're not suddenly confused what it is, right? Our brains do geometric invariance with no problem at all. It's very, very difficult to get computers to do that. In my own career, I watched scientists try and try. I also tried. We went to many conferences, and deep learning just kind of does it. And we don't really know how. There's this network, you give it lots of training data and guide it with the answer, and then it works for new data that you put in as long as it hasn't overfit. So this was a huge win, and it began to tell us, wait, there's something special about these deep learning networks, and they're mimicking what the human brain can do. And even if you change the type of dog, right, you can still get the correct output. Very big deal. So in deep learning, there are basically 4 elements. One is the data set, and you need lots of data. And that Fei-Fei Li's group putting together ImageNet by crowdsourcing was a game changer, because before that, computer vision labs would generate their own data sets. I had a data set in my PhD work that was 9 gigabytes. It was enormous. And lots of people all over the world, you would ask me for that 9 gigabyte data set, and we'd send it all over. And each robot vision lab, each computer vision lab had their own data sets, and sometimes they would share them so we could test our methods on other people's results. But getting data was left to the graduate student who was doing their PhD. Fei-Fei Li's group had this idea of crowdsourcing it and gathering data from the internet. And now this doesn't seem like such a new thing, but back then it was a new thing. And their data set was 1 million images and 1,000 classes. And it changed the ballgame for image recognition. It changed the game for image recognition. And the classification results went down initially, but then when deep learning networks were used, the results went up. So it is still the case that having a data set powers deep learning. And so now we know that data is gold. There is a reason why you have to click on all the traffic lights or bicycles to get into a website these days. And it's not to prove you're human. It's to give them free annotation. You do 2 typically. One, they know the answer to, and they're checking whether you got the right answer. The second one, they don't know the answer to. It's an unlabeled answer, and you're giving them the answer. You're annotating the data set. The company reCAPTCHA had a very interesting business model. So then there's the architecture. How many layers it was the original goal. Now there are transformer architectures which power a lot of modern AI. So wiring up this network in a way that gives good results is why people are getting multi-million-dollar salaries in these big tech companies, the ones who really have the intuition for how to build those architectures and how to train them. Sadly, we don't have the science to map which architecture you need to get what performance. It is very much a trial and error age. And I suspect for the people just in high school right now, you will probably be the ones to develop the science behind how to develop and design a deep learning architecture. It is an unknown, and probably a lot of energy is being wasted on this trial and error mode that we're currently in. Okay, then there's this thing called a loss function. I won't spend a lot of time on it, but the idea is you want to be right as many times as possible. So if you're doing image recognition, you have this data set where you know the answer, right? And you train your network to get the answer that you already know. And the error function, the difference between what the ground truth is, the answer that you know, and the output of your network, that error function is called a loss function. Now, it's not interesting to only get the answer you already know. The magic comes from when you give it new data and it gets the right answer. And if it's doing machine learning, then when you give it new data, it will get the right answer. Sometimes when you train these things, it does great on the training data, and you give it new data and it does a terrible job, and then it hasn't learned anything. But think about how we learn as children, right? We're shown certain things. Maybe our parents showed us pictures of a duck, and several times in our storybook, and then we go to the park and we see a duck, and we didn't see that. Our parents might not have told us that that was a duck, but we know it's a duck because we recognize it. We did the training worked, we learned. And then there's optimization method, which is where the math comes from. I like to think of this as a board with lots of knobs, and you have to tune all the knobs, get all the parameters right so that your network works for the training data. And then that same network, don't touch any of the dials, you can bring it out to the world and it will do useful things. And that's what the big tech companies are doing. They're not literally changing knobs, it's all done computationally, but that's a good analogy for it. Okay, so I've mentioned vision a lot, but the exciting thing of the moment is that vision, NLP, and robotics action are kind of being unified. For a long time, the question about where were things 75 years ago and 50 and 30 and so on, these were separate silos in universities. And if you decided to specialize in natural language processing, you might go to a few talks in computer vision, but the jargon was different and you didn't really understand what was going on, probably. And people created silos and said, well, computer vision does perception, and natural language processing does communication, robotics does action. These are three different goals. But it turns out that all of them use the same deep learning architectures now. And this is shocking to me, right? This is shocking to me. This transformer architecture applied to all three fields works better than the traditional methods. So when things begin to work, universities, we try to get things to work. But then once they work, industry tries to scale it up. So deep learning at scale is called foundation models. And ChatGPT is a foundation model. It was trained with a massive set of data, all of the internet. There are certainly ethical issues involved now in what can be used as training data. But when these models are trained, they are called foundation models. And the hope is that they are used and you don't have to continually retrain. You can fine tune these foundation models. So there are foundation models for large language. There are now foundation models for computer vision. My students in my lab will go and get these foundation models. A lot of them are from Meta and use them. Google VIT is another common foundation model. And what is happening now in the last 2 or 3 years is the production of large action models. So how will large foundation models change research and innovation? It's already changing things. We're using these to as a first step. And see, in this slide, I have specific examples: ChatGPT, GPT-3, transformers. GPT-3 was this great paper that I used to have the privilege of telling my students about and showing them the input and output, and their jaws would drop because ChatGPT hadn't yet been released to the public. Now it's really hard to impress my students. They've seen it all. Segment anything is something that you may or may not have used, but you can now create image segmentation, a semantic segmentation where things are labeled by just downloading code and running it. And same thing with object detection. So here's the large robotics models, as I mentioned, are happening today, and RT1 and RT2 from Google, one of these foundation models. So this slide shows videos in the panels of RT1 from Google, and this is what's happening inside these companies. Many robots in all sorts of mock-ups of kitchens and other things doing tasks. The phrase that I really think characterizes the state of the art in this world of AI is demonstration is the new annotation. We learn to recognize with these enormous image sets that were annotated with what the object was. This image is a dog, this image is a traffic light. That was annotation, and it's still very useful. But demonstration is now the new annotation, both human demonstration and robot demonstration. Okay, but deep learning can fail in surprising ways. So this is the image of a school bus, right? And this early paper said, what happens if I perturb that image? What changes would make the deep learning network fail? So in this, they showed you can add image noise. That center panel shows the image noise amplified a lot so that you can see it. But it's actually just small amounts of image noise, small pixel values. Add it to that image, and you get the image on the right. Now, every human here would still say it's a school bus. Matter of fact, the noise is imperceptible, so nothing's changed. What are you talking about? Why should I have to say it's a school bus again? The deep learning network said it's an ostrich. So this paper was in 2013, so we've come a long way. But at that time, the community realized, wait a minute, adversarial attacks are a big deal. You can attack the thing, and your deep learning system can fail. Additionally, just in general, without adversarial attacks, you just don't know how things are going to fail because they don't fail intuitively. They seem to act like a human brain when they get the answer right, but their failure modes are unexpected. And that's a problem. Right? If we're going to use this for action in the real world, the fact that they can fail in surprising ways is quite scary. So socially cognizant robotics has never been so timely. I run a program at Rutgers called Socially Cognizant Robotics. If you just do robotics.rutgers.edu with nothing else, just robotics.rutgers.edu, you get to our webpage, so you can check out this program. It is a national research traineeship, so we got it started with a grant, a $3 million grant from the NSF. And we started it in September 2020, in the first year of COVID, so that was tough. The only silver lining is that the program really wanted us to meet with deans of multiple schools within university several times in that first year. And the deans always showed up at the meetings. So we were all home at Zoom, and now they don't come to the meetings so easily. So what is socially cognizant robotics? Well, traditional robot design emphasizes typical engineering metrics. As an engineer, I'm very comfortable with these metrics. You optimize speed, accuracy, precision, robustness, and cost. Socially cognizant robot design, you optimize traditional metrics and human-centered metrics. And we collaborate with psychologists and urban planners to help us understand what human-centric metrics are. When I first started this program, I was very naive, and I kind of said to my social science colleagues, okay, what are the human-centered metrics? What's the equation? Let's start programming them in. And they said, no, that's kind of not how it's done. But rather, there's this understanding that you have to get feedback from humans, either synchronous or asynchronous, but understand whether the humans like the robots. And over time, this group, this multidisciplinary group, came up with 4 metrics that we're striving for in socially cognizant robotics. First and foremost, improve the quality of life of people. It seems like a very simple thing, but when you start a project, especially in robotics, is this improving the quality of life? Mitigate unintended negative consequences. So engineers like to say, oh, my project will do this, and it will do this, and it will do this, and will do that. If you stop and say, let me list all the things that could go wrong, right? Be humble in design, then you have a chance to mitigate some of those unintended consequences. But it takes purposeful time to do that. Then we feel like you should enable robots to adapt to humans. We're living in this world. We have a particular way of living our life. And it would be nice if the robots of the future adapt to us rather than making everybody change their way of life to adapt to the robots. And the robots are coming. So these are the kind of things that we kind of need to always have in our mind. The next is respect human autonomy and agency. So we'd like to have some autonomy and agency. Right? I'm kind of fine if my robot cooks me dinner 2 or 3 times a week. I'll give up that. But how many of us would be happy if we were told, starting such and such a year, you're not really allowed to drive anymore because the robots are going to do all the driving. Right? Or something simpler. This new building will have lights, heat, and door access completely controlled by AI. Don't worry about it. The humans don't have to trouble themselves about that stuff anymore. Right? It's like it's something that takes away our agency, our autonomy, and we want to turn on the lights when we want to and shut off the lights when we want to. Okay, so this program is multidisciplinary. We have fields from robotic embodiment, control, computer vision, language, behavioral science, and planning and policy. So I encourage you to take a look. All right, so now I want to talk a little bit about robotics at Rutgers, some of the specific projects I'm working on. New Jersey has beautiful cranberry bogs, and I collaborate with plant biologists at the P.E. Marucci Cranberry Research Center, in particular Peter Outemans. And we've been collaborating since 2019 in merging computer vision and plant biology to help the cranberry growers. So we have we just finished a project that was USDA funded to help the cranberry bogs in New Jersey. And what's our problem statement? Our general problem statement beyond the original grant is to use drones, robots, and AI. And with that, farmers can map entire fields at the berry level to identify stress patterns that are invisible to humans. Right? They might be happening in a very subtle way, or they might be happening over time. So traditional sensors and human eye is a little bit difficult to work with. And this goes beyond cranberries to blueberries, wine grapes, and more. And every year, farmers lose billions to crop disease if we look globally. And it's getting worse with changes in temperature. So what if AI could spot these outbreaks before they even start? This is one of our deep learning networks. Right? So it looks complicated, but at its core, there's a weighted average in there. Right? But we had to design the architecture to make it work. And what we were originally doing was segmentation, looking at those cranberries to find out what's happening with them over time and what's happening with that bog, how many are exposed to the sunlight in hot summer days. So this is the result of that early work. You see those cranberries are kind of hard to detect visually. Right? And certainly, even if you could detect them visually, it would be tedious to go through and count each one or delineate each one so that you could analyze its appearance. So this automatic segmentation algorithm was very useful. In the past, I've also done bridge inspection robots. So this is the Rutgers University Rabbit robotic assisted bridge inspection tool that can go across the bridge and measure cracks at a precision and a frequency that would be difficult to do by a human operator. And measured it both camera and underground sensors. Another project that I like to talk about is teaching robots to feel, give them a sense of touch. So this was with a student of mine, Matt Puri. If you touch a material, right, you have a sense of what it feels like, right? And there are some robot sensors that can do that. This is a Sin Touch sensor. But we can also look at a material and have a sense of what it feels like. So that's what we tried to do in this project, take images of materials and map them to the touch sensor's output, but just using the visual. And so there are a couple of fun science articles that came out of this in the popular science. Robotics in industry. So where are we going to see robots make a difference? One of them is robot exoskeletons for increased strength, increased mobility, less strain and stress for physical jobs. Exoskeletons debuted at the Ford factory some years ago, and I don't know if it's full adoption yet, but the promise of enabling people to work their physical jobs without the typical strain that happens over years is very exciting. So here's Ford's ExoVest. And so a small slide-on vest that just increases strength. I would like to increase my strength. Robot exoskeletons can help people walk. This is a startup company. This is an article from the MIT Technology Review. Again, a wonderful application. How many have seen this video? It's been around for a few years. This is by Engineered Arts. So it's very impressive because the facial expressions give the impression that there's true intelligence going on here. I think it's mostly the fact that the degrees of freedom in the facial expressions give us that impression, but it is not general AI. It's more of the engineering feat of creating that. And here's our dancing robots. How many have seen this video? Yeah, this one's pretty popular.
Didn't even want me around. And now I'm back to let you know I can really shake them down. Do you love me? I can really move. Do you love me? I'm in the groove. Do you love me?
That's exciting. If robots can dance, they must be able to do a lot of other things. But here's one that's a little bit more. my colleagues showed me this the first time in the introducing soft robots and how compliant robots can potentially help that. So when we talk about robotics starting to work, starting to fail in real scenarios, and this issue of robotics and humanity, some key questions: will robots replace people? It doesn't look like it's imminent, but we are seeing robots being able to do tasks that they never could before. And Waymos are probably the biggest robot application that we can point to that's changing our lives already. If you've gone to San Francisco or Arizona or other places where these Waymos are, they're here. So scientists and engineers must consider people when designing robots. And considering people means keeping people safe, ensuring privacy, and preserving human control. So a discussion point is, I actually want to show one more video before we start the discussion point. So here's our humanoid robots. This is Unitree. I said our, but it's not anything to do with Rutgers. It's Unitree humanoid robot. It's just a demonstration of some of the things, how quickly we've come with humanoid robots. But this is the Olympics, the robot Olympics, not the Olympics that are going on now.
Not your average sport.
So this is the World Humanoid Robot Games, the first one. I suspect we will have them each year. And mostly these are teleoperated. You see the operator there. So it's not even AI yet when there's a human teleoperator. But some of them aren't teleoperated. But do look out for this for next year as well. And okay. So again, before we get the discussion, I want to plug Rutgers Day. Rutgers Day is coming. It's an open house for anybody in the New Jersey community who wants to visit Rutgers. And here's some images from Rutgers Day over the years. My students have robot demos. Rutgers is an enormous university, so there's all sorts of demos from all sorts of departments. So please mark your calendars and come to Rutgers Day on April 25th, 2026. Okay, discussion. What do you want to see in the future of robotics? So before I take general questions, I'd love to hear, and we'll just shout out. We'll do the general questions more formally, but does anybody want to say what they want robots to do for them? House cleaning. Others? House cleaning. Predict surfing patterns. Interesting. Walk your dog, yeah. Nobody says shovel the snow? Shovel the snow. All right. So now we're up to questions. Thank you, everybody.
So if you'd like to ask a question, a couple possibilities, queue up in either of the aisles, and we'll just go back and forth between each side. And then we'll also, for those of you trapped in the middle or where else, we'll run a microphone. But go ahead.
Testing. Okay, so two things. One, the word robot's one of my favorite words because the meaning in Czechoslovakian means slave.
I didn't know that. How interesting.
Yeah. Second thing I thought was interesting, what you were talking about agency and humans. And when I've used AI to help me and it does too much of the work, I don't feel fulfilled. I feel like I need to overcome and fight it. Like I do a lot of writing.
Yes.
and I want to like make it really good. And it's interesting how
Yes.
that need for involvement gives you a sense of like it's mine.
Right, right. And from what I understand, this is something we're all trying to struggle with now, so I don't have any answers. How much should we use AI in our lives? I love it for grammar correction. I find it's mostly, I love the term AI slop after that. But I have been asking it for things in technical papers. Show me a paper that talks about this. And I'm surprised how that collaborative effort is very, very good. But you speak to not being satisfied by the engagement. There have been recent studies that talk about how you don't retain the information. If you write something, but then somebody asks you about it a couple of days later, and your writing was with an AI assistant, you didn't retain it and you don't really understand it, depending on how much that assistance. So those are interesting issues.
Yeah.
Yeah.
Thank you.
Go to the other side.
First of all, thank you so much. It was a really fun lecture to sit through. You touched upon reinforcement learning in robotics just really quickly. And I wanted to ask if you like really use reinforcement learning with your projects, like on or off policy or model based or model off, and like how you use it really.
Yeah, so reinforcement learning, we do use, and one of my favorite themes is human in the loop, humans interjecting to to kind of change the reward function.
Yeah.
And then we have a recent paper about learning from videos. And there's an entire offline RL work that we've been inspired by. So reinforcement learning is learning by learning from your mistakes.
Yeah.
And I think it's interesting how it comes from psychology. And we as humans need to learn from our mistakes, and that's how we really learn. And we're seeing that reflecting in robotics too. But to answer your question, I want to repeat again that I personally am most excited about the human in the loop fine-tuning, RL with human feedback.
Yeah.
Yeah.
Thank you.
Yeah.
I'm happy to report that I can still tell in my lab when GPT has been used to write something. I don't think that's going to last very long. It still fools me sometimes. But one of the most interesting robots in human history is the one that just left the solar system. It was built in 1977. And I know that they've reprogrammed it a lot of times to do new things and everything else. And that raises the question is, when will robots be able to do or what living things do, which is to evolve and change themselves?
And change themselves. Yes. That is a deep question, and I don't know the answer to that. I have seen talks about robots that can modify themselves, but it seems to be very, very preliminary. But one thing that is more active, that is sort of in the same line of research, is continual learning. So even if they're not evolving their physical form, how do you create robots that do what we do, which is continually learn without, and this term is catastrophic forgetting, right? We continually learn, yet we know our ABCs. Right, so there's this element of learning what you need to, but not forgetting what you need, and to give our AI systems that capability is a challenge and an interesting one of today. Thank you.
Hi, thank you. Very interesting lecture. I wanted to talk to you about more of the philosophical aspect of AI. So I've heard your lecture where you showed us the dog and how the deep learning was able to pick it up, and we don't understand why.
Yeah.
And I've seen videos and attended lectures with our scientists who have built these systems that are saying exactly the same thing, that we don't understand why it's doing that, but it is doing it and it's behaving like a human being. Now, for me, science is all about fact-based, and science is all about us understanding exactly what we're doing. And nature and maybe philosophy and religion is all about, we don't know, but this was the larger creator. And that's why gravity, for example, behaves why it is. We don't really exactly know why. So the question is, we as human beings are now creating systems that we don't understand, like the creators don't understand what it is, and we're commercializing this on such a large scale. Is there a risk, and do you feel a sense of maybe being scared of what that outcome might be? Because we're seeing these systems behave, but we as the creators don't understand why they're behaving like that.
Yes, yes, I am surprised, and yes, part of me is scared, right? I toggle between optimism and fear. So when deep learning first became prevalent in my community, a lot of the scientists I would hear at conferences say, "We hate deep learning. We're not writing papers. I'm never writing a paper with the word deep learning," I heard a prominent scientist say. He since has. But the fact that it's a black box and you don't really know what's inside, you put data in, you look at its output and train all the weights. And here's something that I didn't mention in the talk. Then often you take those weights and use it as the starting point of a new system with a new data set. And then somebody takes those weights and puts them in a new system with more training data. Eventually you get I call them the weights, but it's the neural network that came from somewhere, and you don't even know what the training data was. Like human beings, you don't really know how they were trained. You look at their resume, where they went to school, but you don't really know their background. So we are creating an unknown. And that's something we have to realize, that there is an unknown, there's a black box component. So the challenge for scientists is to probe and look at the behavior in a way that helps us predict how it will behave. But we're in uncharted territory. Yeah.
Thank you.
Hi, Professor Dana. Thank you for the presentation. It's wonderful. From a layperson's point of view, I had a question about the cranberry bog image, where part of the berries were obscured from the vision, and so the technology is what is it something that detects the density of the berries that aren't visible by the human eye?
It's a black box. We don't know what it's doing.
Really? Really?
It's true. Yeah, it is a neural network, and we developed it to work with just a small amount of annotations.
Right.
We annotate it with point clicks.
Okay.
We also annotated berry-wise to check our results. And then we created a neural network system that would take the true answer, where the point clicks were, and give that answer.
Okay.
And we modified the neural network system to use certain clues that we thought would be useful. One of them was convexity, to have the output be convex. So we did use that.
Got it.
But other than that, there's no look for density, look for this, look for that. There's no if then else rule structure.
Right.
It is giving it data, modifying it. And I can't trivialize that was a skill developed. A grad student, Perry Akiva, who was key for that, another student, Faith Johnson, who would train these networks and have an intuition for how to create the network to make it work.
Right.
But it's all a matter of creating the network,
Yeah.
not using semantic rules.
Got it. And the intuition, I understand, but what about, does it read the color of the berry? Does it?
So we suspect that part of that is the color, but we
Okay.
haven't programmed it to look at color.
Wow. Pretty wild.
Yeah.
Thank you.
Hi, it's great talk.
Yeah.
I found it interesting that, like in one of your early slides, you've got this triangle of AI. You've got vision, you've got robotics, you've got language, and from like a history standpoint, you don't have ethics in that diagram. And I know you know this stuff because you actually cover it and start talking at the edges of it. And like, so on, I think slide 28 or 29, you quickly go like, oh yeah, these rules similar to Asimov. And I'm like, So
Yeah,
it's like, it's there.
So the original, I'm sorry, finish your question, yeah.
But the question there is really kind of about I think you did the right thing of downplaying it, but it's something that we are really beginning to struggle with, because if you like look at Elon's problems with Paris right now, it's something we cannot ignore.
Yeah. So this is a very good point. This lecture is about what is AI. And so that three triangle was what is AI. But what to do about AI, how to make an application, the ethics is key, and the socially cognizant robotics is, and we have a white paper in archive called Socially Cognizant Robotics, where we attempt to create a framework. And I think this is work in progress for the entire society. So that framework is like a start of how to develop a system. And because there's no human-centered metric, that framework talks about asking 10 key questions. My colleague, Clint Andrews, when I told him, there's no equations to optimize, how do we do this? And he talked about this approach of asking questions as part of the pre-design. Yeah, so I agree 100%. It's a very good comment. Thank you.
Thank you again for your time this morning. Can you tell us your thoughts on open access versus pay to play?
Open access, you're specifically talking about
AI's availability into open source versus pay to play.
I am, in my particular subset in computer vision, I'm pleased to see that so many of the models are open access. And as a scientist, that helps me build upon that. I can no longer compete with these large networks, and it doesn't make sense to me for me to retrain them. There's also an energy conservation benefit, where if I can use something that was trained, then I don't have to retrain it, even if I could get the resources. So it's something that I enjoy as a scientist, and I hope continues. But it is in the hands of everybody.
Thank you.
So when you were talking about the cranberries and the computer analyzing the cranberries that humans couldn't really see, that were like obscured by shadows and other objects, so AI can solve that stuff that isn't really capable by humans because they can't see it. But problems like, does space go forever? Does it end, like outer space? Does it go forever? Does it end? Does it loop? Do you think AI will be able to solve one of those problems someday?
Oh, that's a good question. I need to be a physics expert to answer that. But it does bring up the fact that AI scientists are now collaborating with biologists, with physicists, and trying to answer questions that were unanswerable before. One of the examples is protein folding. Came a long way with the help of AI, AlphaFold. But these are the things that we'll find out about. That was my son. He asked me the hardest question.
All these people have such interesting questions. I was wondering why schools don't like AI.
Schools don't like AI. Oh, okay. So now I have to put the teacher part of my professor hat. So I used to be able to give assignments in programming and writing and be pretty much assured that it was the students' work. They might have gotten one of their colleagues one of their friends to help a little bit, but for the most part, I'm pretty assured that it's the students' work. Now, evaluating how well our students understand the material is the challenge. And it's a real challenge. I was moving away from pencil and paper exams in my class several years back. Now it's back. Now it's put your books away, put your calculators away, take your pens and pencils out in college. And because of the struggle of how to evaluate whether students understand it. Yeah. But it is a tool too. So we are discovering what the right way to use AI is, and we're not there yet.
Yeah, thank you so much for speaking this morning. It's a wonderful presentation.
you.
And I was just curious, as an expert in this field, along the lines of some of the earlier philosophical questions and the framework you mentioned of questioning, I'd be curious to know what you think some of the most pressing or pertinent ethical quandaries and considerations that have come up as we develop these systems are. Is there anything in particular that you think might be worth paying extra attention to, especially as we see in the news, a lot of things going unchecked can have sometimes devastating consequences?
It's hard for me to point to something specific. Let me think about that a little bit more, but immediately I think about the overarching need for humility in design. You started your question saying you're the expert, and I think that all of us in AI and engineering should say none of us are expert. This is uncharted territory, and we have to have humility in design. So some of the specific ethical problems, privacy is a very big deal. That the fact that just from our face, a database can be pulled up of not only who we are, but everything about us, where we live. This was always public information, but in order to find where somebody lived, you needed to go into a library and look on the microfilm or something. So it was essentially private, and now it's not. So these are things that are a problem. So, and we also have the problem of getting it right in terms of not moving too fast, and potentially regulating. But if you regulate too much, the rest of the world develops things, and you don't. And so I don't know where that Goldilocks point is.
Yeah, thank you so much.
Thank you for your presentation. It's great food for thought for those hungry brains. So thank you for that. You mentioned about the large models, the large language, vision, action models trained on a lot of data to do variety of things. And then there are also small task-specific models coming up, which are not consuming that much energy, doesn't require that much data. And from your vantage point, where do you see the future of these models going? Do you see more and more large language models maybe consolidating into one or two from big companies, or thousands and thousands of small models democratizing this space?
Well, there is a big push for general artificial intelligence, artificial generalized intelligence. I often find myself thinking, why are we trying to do generalized intelligence where there are so many applications that need solutions? And if we concentrated on specific solutions to many pressing problems, like the need to help a home care giver lift somebody. The fact that there isn't a device that everyone can buy, that of course you can lift somebody who has fallen, even if you're not strong enough. The fact that that isn't a consumer product, that's bothersome. And I'm just giving one specific example. So I am surprised that there's so much emphasis on trying to find this human-like intelligence for generalized problems. Perhaps the argument is that if you found that, you would find the solution to all of these problems. But we don't know. It might not be achievable. The other thing that I thought about when you mentioned that is sometimes from a student point of view, we learn all of these large tools, and I find my students using a big deep learning network for a little problem. And I say, wait a second, in the 90s, we developed support vector machines, and they work really well when you have a small problem with a small amount of data. So we can't lose sight of the small tools that work, that are low cost and low energy and the like. So I'm not sure if I specifically answered your question, but those are my thoughts in the realm.
There's a variation of that question on Zoom right now, which is, and I'm going to paraphrase it, but are you seeing cultural differences in some of these large language models depending upon what country or what area of the world it's being developed versus similar to what he's asking, it's becoming one just sort of set of learning certain behaviors?
Okay, so I don't have an answer to that. I haven't studied it, and I don't want to give the wrong answer. It does remind me, though, of something that I recently read, that Waymos are becoming more aggressive in driving, and that a Waymo that was trained for aggressive city driving doesn't belong in suburbia, and that shift wasn't necessarily made. And it reminds me of the fact that there are nuances that we might not necessarily realize. The humans might say, well, if a car can drive, it can drive. Yeah, so the need for localization of these models to be appropriate for the environment that they are deployed is a real need.
Do they learn how to drive like we do in New Jersey?
Hi, thank you for this awesome presentation. I was wondering if you could speak about the environmental consequences of AI, especially when used in the magnitude that it is right now.
Yes, so that's not my area of specialty, but it is certainly, being a human on this planet, an area of concern. They require large amounts of energy to train, and this is one of the reasons why we hope that when you have a foundation model, it gets reused as opposed to retraining. But it is a major problem, and I would like to see more of an emphasis on efficiency of this training to halt or pause the high use of energy. Yeah, but thank you for bringing that up. It is a crucial point.
Thank you.
Yeah.
Hi, thank you for the presentation. But I was wondering if, how could AI be applied to public transit, like trains or buses or just New Jersey Transit?
Oh, wow. Yeah, that's a tough question. I'm trying to think of all the things that are wrong with New Jersey Transit and how a robot could save. What time is it? We don't have time. So that is interesting, because in a lot of ways, a train's job is just to run on a track. So in theory, you wouldn't need a lot of artificial intelligence to do that. But they don't seem to work. They break down a lot, and then the money needs to be there, and it's an infrastructure that should just work, right? And it's another question, if we're not getting the basic infrastructure that should just work, why are we going for the more advanced infrastructure? Again, a crucial point that I'm glad you made. Perhaps the nuances of measuring conditions that lead to failure in breakdowns, that could be an AI problem to solve. Looking at all of that putting sensors, looking at all of that sensor data and predicting failure before it happens. And then having a situation where things are fixed before they actually break, because for some reason the people in charge of the money might listen to the AI algorithm saying it's about to break. Yeah. It's a great question. Thank you.
Thank you.
Thank you for your presentation. My question was similar to the young woman before us. They're putting a big AI center. I live across the river in Bucks County, and there's a lot of political pushback. They're worried about the electric grid, and they're also worried about the water that I don't understand that are used to cool the chips. So what is the solution? Is there anybody working on these problems?
Yeah. In my work, we don't cover the solutions to that problem. So I don't have a expert answer to that. And I think as people living in the community, we have to use our voice and say that this isn't okay.
Why does they require a lot of water? That's what I don't. The electricity I can understand, but the water I don't.
All factories need a source of coolant. Yeah.
Thank you.
Thank you for bringing that up. Again, such a crucial topic, and that the fallout of AI being developed without thought to, are we improving quality of life or are we taking away quality of life? These questions that need to be thought and need to be talked about even before. In the socially cognizant white paper, socially cognizant robotics white paper, we talk about a process of design, and some of those things should be asked before the implementation of these, and hope they are.
Thank you so much for the talk. It was very interesting. I heard about this one paper in which the computer scientists used models to predict physical behavior. Like, for example, I believe one of the examples they used in the paper was like balancing things on top of each other, and they had a regular physics simulation do it, and then they also trained a model to mimic that physics simulation for higher performance. And I was wondering if this is applicable in your area of study for embodied robotics.
Yes, so simulations, in embodied AI, working in a simulator first is very important, because instead of having a real robot out in the world doing 1,000 trials, bumping into people and things like that, you can go into a simulated world. The other thing that you touched upon was a physics simulator that uses physics versus simulators that are generating physics by black box, end-to-end systems they're called, where the laws of physics are not used. And there is current debate about whether the end-to-end is the right way to do it, or break it down into components and use what you know, the physics that you know within. It is two competing schools of thought. But at a very, taking a step back, it is interesting that you can create networks that give you the output of laws of physics without using the laws of physics, with just observing the inputs and outputs. And you have a network that then simulates Newton's law. So where is the boundary? Where do we use what we know? And where do we just create end-to-end systems that are unpredictable? And I think the way we're going is a hybrid of those two. If we don't know the rules, that end-to-end makes a lot of sense, but possibly where we do know the rules, we can go in and interpret what's happening and fix things. Yeah, so thank you for your question.
Thank you.
When I think about how AI integrates with humans, has there been work about, well, also thinking about maybe this is very much an Asimov do no harm kind of rule for robotics and AI. Has there been work in deciding maybe not the safest way to do things, but pick the least harmful way to do something? So you might have a choice, one choice and another choice. Neither one is good, but I'm going to pick the one that does the least harm.
Yeah, I don't know of any definitive work where it's been discussed and the solution has come about. But certainly that topic drives, and that question drives these thoughts of socially cognizant robotics and other ethics in robotics.
Because there's a system now in that's being developed in airplanes where if the pilot dies, you push a big red button and the airplane automatically finds the nearest airport and goes ahead and lands. But then you'd think, well, if it's an AI system, if there were no airports to land, where would it land? Is it better to land, I don't know, on a beach or in the water, for example? Picking a solution that it's not good either way, but you got to pick the better one.
Yes, so in the design framework and the consideration of unintended consequences, the thought, the framework that we propose is that the unintended consequences be enumerated and discussed, and that there's feedback from all the stakeholders. Right? So it's critical that individuals don't get to decide these things, that they get thought about and discussed among all the stakeholders so that we make the best decision. The best decisions are often made with groups of experts and non-experts being polled and discussed, giving feedback as well, especially when where they're being directly affected. Yeah, so.
Thank you.
I'm trying to teach my students in engineering the design frameworks that think bigger than the metrics of speed and accuracy, and cost.
Yeah, thank you.
Thank you so much for such a great presentation. So I have two questions. One is there's a lot of like AI generated like content and like even images. Does this data kind of fall into your data sets that people use now? And also like do you guys also do like you do image detection? Do you recognize or like detect AI like images and then going further into like deep fakes, stuff like that?
So, okay, so there's multiple ways to think about it. So, the contamination of what is on the internet with deep fakes is here and it's not going away, and that's a problem for all of us. So the crowdsourcing that was done to create ImageNet wouldn't be able to assure that some of them weren't fake. And the image features in deep fakes are different than in real images, although they're getting more and more indistinguishable. So it's a real worry, the contamination of the internet. And when you roll out the timeline, the question that we have is, will the internet just get more and more contaminated? The need for provenance of where an image came from and who generated it and can it be trusted? We're addressing that with watermarks, and this company that I co-founded with a PhD student of mine, Steg.AI, is trying to create methods that give image provenance. So very soon we are getting to the point where we won't take an image just and trust that it's an image. It's fine. It's real. Maybe we're here already. And so the up and coming thing is to be able to digitally watermark those so that that you can have some level of trust. Yeah. Thanks.
Thank you so much for this lecture. My main question is, currently in our lab, we're working on like an AI for drug discovery. And one of like the problems I saw with like a lot of the pharmacy professors, as well as biology professors, is they don't trust the results as much due to the black box. And because like they wouldn't know what the AI, why they picked certain like molecules. And this was also in one of our class, we saw that they were talking about the legal ramifications, for example, loaning a house, how they don't know if they picked like a certain person because of some aspects that would be legally like illegal, like race or other things.
Yes.
Is there a way to minimize this black box? Because I know there's no way to like completely know why the AI picked that.
Yeah, so there is a field called interpretable AI where we're trying to minimize the black box of AI. So I don't want to give the impression that there's nothing that can be done. There's an entire field it's a pretty new field of trying to explain the AI decisions, but it's a very imperfect field. It's not like, oh yes, people wrote papers about it and you just use their methods and everything's fine. So trust both in the research and in the research domain, in financial domain, in medical domain, it is an issue. So what do we do? One of them is to create distill the large black box model to a kind of an old-fashioned machine learning model, like a decision tree, where you can then see what it's doing to make those decisions. But the argument that could be made is, well, that black box model is more powerful than the distillation model, so you would want to use the black box model. So that's the counter argument. But that's where we are so far. We've got some explainability. My own take on it is that human in the loop, having the ability to correct, having basically experts hold the robot's hand and correct and build these things so that there is observers who watch and correct, parenting the robot, so to speak, is a reasonable way to go.
Thank you.
Yeah.
So this is about the cranberry model that you have. there's a problem in image recognition that I'm sure you're aware of, where you can train your model on the wrong thing. So the classic problem of, I've got these images, I'd like to train a model to recognize dogs and wolves.
Yeah.
And so you give it all these images, and what comes out is a model that knows how to recognize living rooms and snow. So do you think with your cranberry model that it may be actually learning in part how cranberries branch, the actual plants grow? And so it's going like, there should be a cranberry here, and I see what could be a cranberry there.
Yeah, yeah. And as a matter of fact, for finding cranberries, as long as it found the cranberry, we don't care, because with the background it's okay if it gives it a clue. And for a long time in computer vision, we understood that recognition, people used context, but we didn't really know how to use that context. And the fact that deep learning does it automatically can be a real boost, but it can also be a problem. In the medical domain, there was an early deep learning paper that mistakenly, they were looking at slides where there were cancer cells and there weren't, and they didn't realize that there was a little marking on all the ones that had cancer cells, and the deep learning network was only looking for that marking and didn't recognize anything about what was on the slide. So yeah, it's a buyer beware issue when you use these neural networks. Yeah.
Thank you.
And with that, if we could thank Professor Dana once again for this wonderful talk.